Maths and the Coronavirus Part 2, An Introduction to Logarithms. I saw an article yesterday on the ABC website that said to understand logarithms you have to be some kind of mathematical genius. Well, honestly, I don't think they're right. Logarithms aren't really that hard, but if it's on the ABC, it must be true. So let's turn you all into geniuses and let's figure out logarithms. First of all, a reminder. Yesterday, we had a look at this little chart, the animation, which shows what happens with the spread of coronavirus if nobody takes proper precautions. Then we had a look at my somewhat daggier version of that same little picture, which shows the number of people with coronavirus going from 1 to 2 to 4 to 8, doubling at every stage along the way. And we looked at how quickly that could turn into some very, very big numbers indeed. And we figured out that the number of people that would have coronavirus, call it y in this demonstration, would be equal to 2 to the power of x, where x is how many stages down the line we are. So at the first stage it's 2 to the power of 1 or 2 people. At the second stage, 2 to the power of 2, or 4 people, and so on. And we gave that kind of equation a name, an exponential equation. Then we looked at a graph that shows just how quickly exponential equations get bigger. Something similar to this graph, which shows the number of people with coronavirus around the world. Notice that famous kind of jump shape towards the end, as it gets steeper and steeper very quickly. If you need to see a demonstration of just how quickly exponential things can grow, try folding a piece of paper. Take a piece of paper, standard A4 paper, it's about 0.1 of a millimeter thick, and fold it in half. Right? It's now 0.2 of a millimeter thick, it doubled. Do it again, and it'll become 0.4 of a millimeter thick. And keep folding. By the time you get to your 6th fold, it'll be about 3.2 millimeters thick if you squeeze it right down again. And it'll start to get very, very difficult to fold. Once you get up to 7 or 8 folds, you'll find it extremely difficult. You might even need a pair of pliers. But even then, it's not that thick yet. Leaving aside the fact that it's probably physically impossible, if you could fold it 15 times, with the thickness doubling every time, then by the time you got to 15 folds, your piece of paper would be 1.6 meters thick, just a little bit short of 5 feet. At 25 folds, it'd be 1.7 kilometers thick. Take it out to 35 folds, and you're about 6,500 kilometers, enough to fill a hole that goes all the way down to the center of the Earth. Take it up to 57 times, and your piece of paper would stretch out past Pluto. And here's the graph. So the number of times the piece of paper has been folded is across the bottom of the axis there, and the thickness of the paper in millimeters is up the vertical axis there. If you're not used to that E notation, that's exponential notation, which means take this number here and put 14 zeros after it. So as you can see, we're dealing with some very, very big numbers as we go up there. Okay, so coming back from folding bits of paper to coronavirus. And here's a version of the diagram we saw in the first video. So we start with 1 person sick, then at the next stage we've doubled that to 2, then we double it to 4, and we double it to 8. Now, one of the most important things that people who want to contain coronavirus want to be able to know is how quickly is the virus spreading. We know that we can't stop the virus spreading completely, but we can slow it down. We can flatten the curve, and you've probably seen that animation a fair bit. So what's really important for the health authorities to know is how long does it take that process to happen? How long does it take to go from one to the next for the number of people who've got the virus to double? How long does it take to double the number of people with the virus? Well, this is where graphs can help. So let's scroll across, and here's the graph we saw yesterday. dates are across the bottom of the graph, and then the number of people with the virus is up the side. So if we work just with this graph here, we could say, all right, there's 100,000 people, and that happened on this date there, roughly. Sorry for that line. Then we go to 200,000, so that's there, and we could drop a vertical there, and we could count the number of days between there and there. And then we could double again to 400, and then double again to 800. But it's not a very easy graph to read, because as we go up this y-axis, it's going up 100,000 at a time. So 1, 2, 3, 4, 5, etc. But if we want to know how long it takes to double, what if we changed this axis? What if instead of going up by the same amount each time, in this case going up by 100,000, what if instead of going up by the same amount each time, we changed it so every time you go up a line, that's double the line before? Let's have a look what that would do to that graph. So there's the same set of data, but have a look at the y-axis. The y-axis starts here at 1. Then when we go up to the next line, it's double to 2, double to 4, double to 8, double to 16, and so forth. And so every time you go up a line, that's doubling the number of people that have the virus. So, for example, if we start at the time 4,096 people have it, right there, and we drop ourselves a vertical down to there, we can say that occurred on that date there. And then that doubles from there to there. So we can take a vertical and drop from there to there. And so it takes that long for it to double the number of people. So that's not very long, that's only a few days. Let's have a look over here. We're starting here at about 65,000 people have the virus, so let's drop ourselves a vertical. And we know it doubles when I go up to that line, but look how long it takes to get to that next line. There. So we can say that over here, the rate was doubling every couple of days. Over here, that's the best part of a month for it to double again from there to there. So that probably indicates that we're doing the right thing to slow the spread of the virus. And the important bit for us as mathematicians is what's going on in this left-hand axis, this little trick we pulled, where we said, I'm not going to go up 1, 2, 3, 4, 5. I'm going to double 1, 2, 4, 8, 16, etc. Let's have a look at that on a slightly simpler graph. So our final part of today brings together what we did yesterday and what we did today. Let's go back to what we did on the graph. And we said, for example, that 2 to the power of 3 is 8. So let's just write that down, because that's a pretty obvious fact. And yesterday, we looked at equations that looked a bit like this. And remember, they're called exponential equations. So, if I tell you in that equation that y equals 8, then what you need to figure out is the answer to this. 2 to the power of what equals 8. Now, the way to figure that out is to work with logarithms. So I'm going to write that statement out in a slightly different way. It means exactly the same thing. Don't let the fact that it looks a bit weird scare you. Log 2 8 equals x. So they are two ways in maths of asking exactly the same question. The question is 2 to the power of what equals 8. This is the same question. Log with the base of 2, remember we talked about bases up here, log to the base 2 of 8 equals what? So, the other way to read that log statement is 2 raised to the power of what equals 8. And so using that statement, we would then be able to say, oh, I've got 128 there. What number should I put there? If I crossed out, what number should it be? And you know by just working up the page, 5, 6, that should be 7. But if I didn't know that, I would ask the question like this. If I get my colour correct here. I would ask the question like this. Log with a base of 2 of 128 equals what? Remember, the other way to write that is 2, your base, raised to the power of what equals 128. Now, if you're thinking at this point, you've probably realised that I haven't actually given you any way to solve that problem. All I've done is written it out in a slightly different way, which doesn't really get you very far. In the next video, we're going to have a look at how we might solve a problem like this and how we use the properties of these logarithms to solve a problem like this.